solutions. Therefore, we're going to find one solution, put into real imaginary parts as before. So we're going to do the same song and dance we did before. But let's start by doing this. We're going to find some sort of little star. Hi. That's me not horsing around. We're actually going to do math. So find lambda. All right, so here we're going to have 2 minus lambda minus 3, 3 minus 2 minus lambda. So this, we set this equal to 0. This implies what? I'll have 2 minus 2 lambda squared plus 9 is equal to 0. This is lambda squared plus 4 lambda minus 13, or plus 13 is equal to 0. This gives us lambda is equal to minus 2 plus or minus 3i. So here we go. All right, just remind me at the end and I'll grab you. Okay. All right, so here we have this. And so, yeah, we get imaginary eigenvalues. So we're going to start finding our eigenvector. So let's go ahead and our next step. So we're going to just find the eigenvector. So right now we're just plowing through like we plowed before, right? We're just going as we did before. I'm going to do lambda 1. And I'm just going to say lambda 1 just to follow what I have as my notes. For some reason, I chose the negative one. I don't know why, but I did. So here, let's find one of these. And so to do this, we're going to have minus 2x minus 3. Oh, I think I did it so the numbers would be easier for you to see that things ended up being the way they were. So here I have x1, y1 equals to minus 2 minus 3i x1. And then here I have I'll have 3 minus minus 2 minus 3i. Okay. And so if I do this, and I move this over, so the minus 2x1s cancel, so I have a positive 3i. Yeah, I see why I did what I did. There's a good reason for it. Oops. 3i x1, y1 equal to 0. And then here I have 3x1 plus 3i, y1 is equal to 0. Now, are these two the same? Are these two the same equation? Yes, no, maybe. The answer is yes. Here, if I take this and multiply this by an I, right? If I multiply all this by an I, so this would be 3i x1, and then 3i squared, becomes negative, and so it'll be 3y. And so these are the same, they only differ by an I. So we'll just, okay? So this is the same, and so you can cross off. Now, honestly, as long as you're very sure about this, you can definitely do this, right? And so what I used to tell my students in person, just cover your eyes, say, yeah, they're the same, and believe it, and cross one off, right? Because mathematically they should be if your eigenvalue is correct. So if you're very sure on this, go ahead and do this, because checking that two complex equations are the same is not a skill that you guys are comfortable with. Just in my experience. You guys may be super comfortable with that, I don't know, but in my experience at this stage, it's not something you're super comfortable with. So here, if we just move this over, I get I x1 is equal to y1. And then here, this gives me the eigenvector of lambda 1, 1i. Okay. All right, so here I have my first solution. And so let's look at my first solution real quick. So here, b1 of t is equal to e to the minus 2 minus 3 it times 1 and I. So this is complex, but we want real solutions for it. So we're going to do the same thing we did last time. So we're going to do the same process. So the same process as last time.
Is it the quantity of negative 2 minus 3i times t? Or is that t inside the quantity there in the e? Yeah.
Thank
Okay,
you.
cool.
Thank you. Thank you. Thank you. Thank you. Woohoo. Why am I writing on the wrong layer? I want to erase. Maybe with this. There we go. All right, so we're going to do the same process last time. We're going to split this into its real part and its imaginary part. And we're going to take this as one. We're going to take this as a solution and this as a solution. All right, so we're going to do the same thing we did last time. And so let's go ahead and split that. So this becomes y1. So y1 of t becomes, and we're going to split this into its real and imaginary parts. So this becomes e to the it becomes negative 2t times cosine of minus 3t. Here it gets a little bit weird, but I wanted the negative up here for this, so it's fine. 3t, multiply all that by 1 and I. We'll go ahead and do that multiplication. I'm going to probably wish I had more room. So let me just strictly stay on this side of the line so I have more room over here. All right, let me, oops, go ahead and put that line back. And let's go ahead and move this over. Oh, I definitely have enough room to do what I want. All right, so let's go back to here. So here we're going to have e to the minus t. And I'm going to go ahead and multiply this into that. And so this is going to be cosine of minus 3t plus I sine of minus 3t times I cosine of minus 3t plus I sine of minus 3t. And technically right here I can do something to save myself trouble, but I'm just going to carry the negative 3 for now. What could I do to save myself a little bit of trouble? I could use the fact that cosine is even and sine is odd and pull out the negatives, right? I'm just going to leave it in for now because most of the time you're going to choose the positive version. I chose the negative version for this, just to make this clear to you guys.
Is that bottom row supposed to be I cosine plus I sine, or is that going to be i's cancel out to make it negative?
Yeah, so it's I squared. Sorry.
Okay, cool. I just want to make sure. Yep.
Yeah, let's just go ahead and cancel it to negative. Is everyone okay with that? That this I and the I becomes negative? Okay. So let's do that. And so now I'm going to split it into its real and imaginary part. So here I have e to the minus 2t. So the real part here is going to be cosine of minus 3t minus sine of 3 minus 3t plus e to the minus I e to the minus t. And then we're going to have up here sine of minus 3t and then cosine of minus 3t. All right, so this is my real part. Everything beyond here is my imaginary. So this is, I'm going to call this y real. I'm going to call this y imaginary. And notice that if this is the solution to the differential equation, which it is, right, or the differential system, or the system of differential equations, I guess the proper way to say it, this is a solution to the system of differential equation, then this will be a solution to differential equation, and this will also be a solution to differential equation, since these parts better add up to equal 0, right? And so it's the same thing we did last time. And so in this case, we're going to get our final solution over here, y of t, is going to be equal to some c1, the real part, so it'll be e to the minus 2t cosine of minus 3t sine, or minus sine of minus 3t plus c2 of the imaginary part, which is right here, which would be sine of minus 3t cosine of minus 3t. And so here we produce a solution. Okay, I'll let you write that down real quick. I have water. That's what I usually do. So I take a drink to make sure I do this.
Would that be just for one of the eigenvalues? Would we have to do it from the positive as well?
No. So what happens is if I choose the positive, um, you can choose either positive or negative. It really doesn't matter. Um, if I choose the if I chose the positive, I would have had a different eigenvalue here and a different vector. I can almost guarantee you this would have just been negative, right? Um, and then when you calculate this through, it would have given you equivalently the same thing.
Okay.
Okay, because this three would come out. So these three would just turn into normal sign. This would be here, but then since I have the minus here, this would have a minus, so you can move the minus up top, and it ends up being equivalent. Okay.
Cool. Thank you.
All right. So let's do which one's 15.
Sorry, one more question on that last one.
Yep.
At what point does it go from y1 of t to the actual y of t
Oh, so
in
here,
this case?
I have y1 of t is equal to e to the minus 2t. So here, this is still y1 of t, right? This at this point, I'm y1 of t still. This is the real part of y1 of t. This is the imaginary part of y1 of t. And so when I make my
Gotcha, I got you,
solution,
got you.
let me make this as kind of a theorem right here. Y of t is equal to y, or c1 y real plus c2 y imaginary. Okay? And so our real part was this, our imaginary part is this, and then we just add the constant in front of it. It's the same thing we did with second order when we had the imaginary answers. If you remember, you just remember just skipping to e to the real part times cosine plus I sine of the imaginary part, and they're just saying one. Then you just said, um, yeah, just kind of like what we did right here, right? We had here I had an imaginary part. I take the real and cosine, and then the real and the sine, and just worked it through. So it's the same thing, the same concept from here goes to here. Okay. All right. So let's do another one, and this time I will take the positive version, and I can show you it does get a little bit more complicated, but let's work through it. It's sadly to say what I just showed you is the easiest way this thing can fall out. um, it's not any more. It's not any harder. It's just more. There's a lot more complication to it, and in the sense there's just a lot more terms floating around. Well, let's do it the same. So here and here, I made it very clear. I put a 0 here. So let's go ahead and rewrite this. So our matrix here is 0, 2, minus 3, 2. So we're going to find our eigenvalues. We're going to find lambda. And so here I'm going to take 0 minus lambda, 2 minus 3, 2 minus lambda. Let's set that equal to 0. That's going to give me lambda squared minus 2 lambda plus 6 equal to 0. And that's going to give me lambda here is 1 plus or minus I square root 5. Okay. The next thing we want to do is we're going to find one eigenvector. We only need to find one eigenvector. So we're going to just say b lambda 1. And one just in this case, I'll choose the positive one just to show that it doesn't matter which one you take. Okay. All right, so we're going to plug that in. So I'm going to get 2y1 is equal to 1 plus I square root 5 x1. And then I'll have minus 3 x1 minus plus 2 y1 is equal to 1 plus, I forgot my square root, sorry. 1 plus I square root 5 y2, or y1, sorry. So that's what this equation is, right? Now, what am I going to do here? Now, is this equation equivalent to this equation? Yeah. How are we going to do this? We cover our eyes and say, I got the right eigenvalue. That's how you guys are going to do this. I almost Could I show it to you? Sure. Right. You move stuff over, then you multiply stuff across. You get rid of complex. It's fun, but it's not. Right. So let's just do this. And so what does this mean? Well, this means that um, so here I actually don't need to simplify it, right? I'm just going to choose x1 to be 2 and y1 to be this mess. So 2 and 1 plus the I square root of 5. There's our eigenvalue. Okay. How did I choose that? I chose x1 to be the coefficient on the y and y1 to be the coefficient on the x. I almost always do this, just makes it easier. So here I have an eigenvalue and an eigenvector, which is complex, and that's all you need. You only need one. So let's crunch on through. All right, so the next part is we're going to find, so let me write this here. So this will be step 1, step 2. So step 1 and step 1 is the same for all these systems. So you're going to find out what the eigenvalue is. From there, you're going to choose, from there it differentiates. For different reals and complex ones, you need to find eigenvectors. And for the reals, you find 2. For the complex, you only need to find 1. Step 3 is unique. So we're going to split. So we need to split y1 into y real and y imaginary. So that's our next step. So we're going to split into y real and y imaginary. So here we have y1 of t is equal to e to the, so this one's positive, plus I square root 5t to that looks like an 8. Let's try that again. 5. There we go. I'm going to split this into the real and imaginary parts. All right, how much space do I have? I better be. I don't want to run out of space. So I think I'm okay, though. Okay, I think I'm okay. All right, so let's do this. So what I need to do, I need to use Euler's formula and convert this over. So here this becomes y1 of, I guess I don't need to write y1 of t. This just becomes e to the t cosine of square root 5t plus I sine square root 5t. And multiply that by 2 and 1 plus I square root 5. All right, so we're going to go ahead and crunch that through. So we have e to the t equals 2 cosine square root 5t plus I 2 sine square root 5t. And then I'm going to do this onto this and then this onto this just because that's how my, so how do I want to do this? Well, let's just do the 1. Let's do the 1. Let's do the 1 first. So let's do this to be cosine of square root 5t plus I sine square root 5t. So I've done the 1. Now I need to do the plus the I5. So I square root 5 cosine square root 5t plus the I onto this will give me minus square root 5 sine of square root 5t. Okay, so that's my vector. That's some big mess. All right, now I need to split it. So let's go ahead and split it. So the split, it's not really all that hard. Just take the real parts. So here the real part up top is 2 cosine of square root 5t. The bottom part, it'll be cosine of square root 5t. This is imaginary. This is imaginary. So minus square root, minus square root 5 sine of square root 5t plus I. And we're going to have e to the t. And then we're going to have on top, we'll have 2 sine square root 5t. And then on the bottom, we're going to have sine square root 5t plus square root 5 cosine square root 5t. So here's my, this is my b real, this is my b imaginary. All right, so from here, so step 4 in this case would be to put it together. So put it together, and so we have y of t. I'll have it. Yeah, let's make this very clear. It's y of t equals c1 b real plus some c2 b imaginary. All right, so in our case, that would be c1 e to the t. I'm so tempted to do something. Because I'm in Photoshop, right? Just like grab all this and just copy and paste it, right? Copy and paste. Oh, look at that. No. I want my pasted layer to be. Thank you. Why is it grabbing that layer? Bad monkey. Ta-da! I can fix it. There we go. Let me just get this. We write on layer 4. So you just copy and paste this all over. You just hit plus C2. Ta-da! I'll give you guys a second to copy that down. Sometimes it's nice to work digitally. I'm going to go grab my water. I don't know where it's at. I know. You can come back in if you want. Go back in the room if you want to call me. Come on, you two. All right. There we go. All right. Did anyone else just draw arrows too? Flawless. No, I'm just kidding. If you draw arrows, I won't be mad. On the exam, please do write it out though. All right, so this is what we have here. So now I'm debating if I want to do something with you guys. Yeah, let me do something with you guys. Let me make this a little bit longer, seeing how we're taking a little extra time to do this. So let's pretend we had initial conditions. We haven't done initial conditions for a while. So let's pretend y naught is, so y naught, or in other words, y of 0 is equal to 1 and 1. Well, how would I do that in this case? How would I do that for this case? Well, I'll just plug in. Let me zoom out. So given this, let me do that in this space right here. I'm just going to plug in 0 for t. So this just becomes, and so this becomes, so y of t becomes c1. So this becomes 2 up top plus a 1 minus a 0. So this is 2 and 1 plus c2. This is a 0, this is a 0, this is a square root 5, right? Does everyone see how I got these vectors if I plug in 0 for t? Okay. Now, if I solve for this, I'm going to get c1 is equal to a half, right? Because there's 0 here, so this one just becomes a half. That has to be true. And if this is a half, then that forces c2 to be um, 1 over 2 square root 5, which isn't all that pretty. And then, yeah, you can just plug these, you can plug in. There, I'll draw arrows this time, not make you guys rewrite the thing for a third time, right? Does that make sense?
So we're just pretty much doing what we did before, except 2 equations at a time.
Mm-hmm.
Okay.
Yeah, and so the second one here can get kind of big, and especially if because one part will be complex at least. So, all right, so let's go to the next page. Someone, all right, most people. All right, so how do we draw this mess? All right, so how to draw this mess? So here, so it's determined on this. So here is determined. So here if we have by lambda, and basically it's all determined by what the real part is. If the real part is 0, if the real part is 0, notice that we get only sines and cosines. And if we only get sines and cosines, we're going to get some sort of circular thing that goes around and around in some sort of pattern, right? And we call these centers. And I'll show you a couple of these. Here, if it is less than, if the real part is greater than 0, and let's see what we have. We'd have one greater than 0. So yeah, so this one's less than 0. This one's greater than 0. Notice here the amplitude on these sines and cosines is going to get larger and larger as this e to the t gets bigger and bigger. And so it's going to spiral kind of outwards. So this one's just going to kind of go out, and then you can just draw another one out. So this one spirals out. We call these spiral sources. And if it gets smaller, the amplitude gets bigger, smaller and smaller, and then it kind of spirals in. And we call these spiral sinks. Oops. Yeah. And then you get happy spirals. I swear my brain doesn't work well. I see these two spirals. My brother showed me the new Saw trailer. I'm like, I don't want to see another Saw, but it's Chris Rock and Samuel L. Jackson. I'm like, I don't know. As bad as those movies could be, this might be just terrible in the right way. Anyways, let's show you how to do for actual examples here. So let's do some. Give you some examples and show you how to do these by hand, and then I'll show you how to do them in that. All right, so let's look at this. So here I can tell you what I can easily. So here we just find the lambdas, and for when you're drawing these, you basically only need the lambda and this. You don't actually need what the vector is. You need the eigenvalue and this, and I'll show you how to do this. So here we have this becomes plus or minus I. This just becomes plus or minus I. So this is a center since the real part. So since the real part here is 0, it's a center. Okay, that means it's going to go around and around in circles. Now, how do we determine which way it goes? So we know it goes in circles, but you should be able to determine the direction. And to do that, you're going to look at the you're going to remember how these things are drawn, and I'll show you what I mean by that. So here, these are perfect circles. So this is center. So we're going to look at, let's pretend I plug in the value 1 and 0. So here if I plug in 1 and 0, what is my change in x and my change in y? Well, if I plug in 1 and 0, this is my change in x and change in y is just this, right? My change of x is 0, my change of y is 1. If I plug in this. So if here I'm at 1, 0, so I'm going 0 in the x direction and 1 in the y direction. So I know if I drew my remember how we figured out how to draw these before? You plug in a value for x, you plug in a value for y, and then this tells you the direction it moves. So that's back to when we first learned how to draw these basically. Now, if I plug in 0 and 1, I will get the function here of this. And so you really don't have to plug in anything. So here at 0, 1, which way am I going? I'm going negative in the x direction, negative in the y direction. So which way is this spinning? Well, this is spinning counterclockwise, right? So I'll just draw in my little circles and I say it's going counterclockwise. And this will be true for this. And it'll be true for the bigger one. And so let's actually look at this in let's look at this in I don't have to. All right. Dang it, where'd it go? Woohoo. Oh, some people said that when you open it up on a Mac, it says it might be malware. You can't open it. The thing I sent you. If you just hold Option, I think it's Option. You can override it. You say, "Oh, you don't want to open this? That's nice. It's fine. Trust me." And you can override it. I think it's Option. It says you downloaded the internet. I don't know who this person is. Trying to infect with malware. There are some things that I don't know. Yeah, it's not. Sometimes Apple's just a little bit more extra safe, which I don't, I'm not mad at, right? um, not mad at it. All right, so here we go, and look, ta-da, perfect little circles. Now, this is a good point. Let's clear this again. So when it draws this, it has these little dark lines. Are these dark lines true? No, it's just the program crashing, right? We talked about numerical artifacts. So here we have this. And so notice that our picture matches what's here perfectly. Well, not perfectly. My picture's kind of bad. Yours might be better. Trying to get us to Bitcoin mine grain. Oh, I should. Everyone should start mining Bitcoin right now. All right, so let's do the same thing here. So here, we did this one, all right? We already did this one. This is one we already did before. This is the -2 plus or minus 3i. So since alpha here is less than 0, this is a spiral sink. Okay, so I know it's going to spiral in and sink. Now what do? Well, I draw my first two vectors. So right here, I have -2 and 3. So here at 1, at 0, 1, I know I'm going to go -2 in the x direction and +3 in the y direction. So it's kind of pretty strong this way. And then here at 1 and 1, I'm going -3 and -2. So -3 in the x direction, -2 in the y direction. So kind of like this. So which way am I spinning? Inwards? Well, I'm spinning inwards this way, right? And so now you know which way it spins. And when you draw these, so when you take the exam, I'll have you draw a couple of these by hand. Which way it spins matters. The only thing that makes me fear about asking you to do it by hand is I know for a fact every one of you will type it in, look at it for real, and then that's how you determine how to make it spin instead of doing this way, which is super convenient and intuitive. But when we have computers, we're engineers. Get out of here, mathematician. Get out of here with your math stuff. we want to do it our way.
We want answers. We want the real answers. We don't care how we get there.
Right. All right. Yes. So that's the end of the complex stuff. Do I want to start real? Let me see what we have ahead of us real quick. Let me see what we have ahead. I'll make a decision. I need to finish for this chapter because we'll probably finish this on Monday. Because if I'm at okay, so yeah, because all we need to do now is figure out how to do the repeated, and we will do it a bunch of times. You're just going to follow this. It's actually a really quick method, and I'll teach you how to draw them, and then we're done. Can you explain the? Oh yeah, let me explain that one more time for those. So here, I'm gonna look. So let's go. Actually, let me go back. Let's go back. Let me go back to explain this correctly. I'm actually opening up the completed version. Where do we draw those phase planes? No. That was on page 3. Let me open up page 3. All right, completed notes. Hold on. Let me finish this because I can definitely do this part. All right, move that over here. Put this in this view. All right, page 3. Wow. All right, so let's go back. I know this is a long time ago in the galaxy far, far away. Who remembers this stuff, right? So remember when we're drawing these directional fields or phase portraits, right? So we just input a number, and then we can figure out which way, and the vector points in which way the solution will want to go, which way the solution tends to go, right? And so here, if I plug in 1 and 1, or 0 and 0, we get 0. If I plugged in 1 and 2, I got 1 and 2, and these just kind of pointed out here. I'm doing this. I'm doing the same thing over here. I'm doing the same thing over here. But now I'm going to start at 1 and 0. Why did I start at 1 and 0? Because the answer, if x is 1 and y is 0, this is 0, and it's just the coefficients on my axis. So 1 or 0 in the x direction, 1 in the y direction, right? So 0 in the x direction, 1 in the y direction. If I put x equal to 0, y equal to 1. So my dx dt would be 0. My dy dt would be 1. If I start at 0, 1 right here in the y, so I plug in 0 for x, my dx dt would be negative 1 because y is 1, and my dy dt would be 0, and so I'd be pointing directly in this direction. Same thing for over here. Here, if I plug in x equal to 1 and y equal to 0, so if I'm starting at this point 1, 0, what is my phase line or my direction line? And so dx dt would be negative 2. My dy dt would be 3, and so it spirals in. And so it's spiraling this way. And then here, if I start here, if I have y is 1 and x is 0, my dx dt is negative 3, my dy dt is negative 2, so I get this kind of vector here. And so you can kind of see which way it spends. Does that make sense how to do that? And then the last thing I need to do, and we'll just call it for a day. We'll have plenty of time to do the other one next time. We'll call it for a day, and we'll just go ahead and just type this one in so we can look at it. What are you guys using besides this in order to make your phase portraits? That way, if people who do this project last minute have something to work towards, if they can't get this to work. I think you might need legacy Java for this to work. And let me show you this quite clearly. So here at 0, 1, notice here that this directional vector is negative 2 in the x direction, 3 in the y direction, right? And notice here at 1, 3, it's negative 3 in the x direction and 2 in the y direction. So that's where that comes from. That's how you determine which way it's spiraling. And here we can say it's spiraling counterclockwise. Okay. And I guess I have it go around more than it should. It's actually a little bit flatter than that.